So you can see this time-lapse video going. We discretize the wing into sections. So there's a bay fore and aft, and then there's a fan section fore and aft. And then each servo or wing section is split up into a single part with various components. So this time lapse, you may not notice, but it's been going for almost 20 minutes. It's about a 20-minute time lapse. So to put into perspective how long it takes to print this aircraft, it takes 3 weeks on 2 printers running 24/7. I did the math once and it's, so I'm not even gonna try to do math while I'm up here. But it's a long time. I think it's about 500 hours for a single airframe. So once again, we split into sections and you can kind of see, I would usually split it into a bay forward section and then a bay aft section and then the fan section. And then I would print each wing segment with its left and right halves. And then of course the winglets, but thankfully those last most crashes. So yeah, any questions about this process? Otherwise, we'll move on and talk about the manufacturing process. Cool. And we get the idea that so I'm going to stop this. All righty. You're up, Josh.
All right. So I don't know if everybody got introduced at the beginning because I've been in meetings all day, but I'm Josh Hurwitz and I am one of the undergrads in this lab. And I was primarily responsible for making all of the cuts and stuff that Ben made go away. So all of these different pieces had to be assembled together and we used a 2-part epoxy to attach them together. And then to make sure that they actually maintained all their strength, because epoxy is only strong and shear, we added carbon fiber rods in that I-beam that you'll see in the I-beam spar. And those carbon fiber rods were soaked in epoxy beforehand to actually make sure that we had the required strength to keep this together. So you can see part of the things that I had to do here to put it together was to remove all the support material that you saw in the printing process that we actually need to keep it together. And so every part had support material that needed to be removed. So if you look at this, it takes roughly 13 hours to do all of the work. And that's in man hours, so you can split that up by doing it more than once, but I did this one pretty much on my own. And so I would glue one piece at a time and then I would go back through and remove more support material to try to make it more efficient. And this one that we did the time lapse on was actually our most efficient one because I believe I got all of the glue done in roughly 9 hours. So some of the important things that I did through here is you have to do surface prep on every single piece because as we've learned, 3D printed material does not take to epoxy well, it's very slippery. So you have to go through and scuff up the surface and sand it and get it so that it's a very rough surface. You get more surface area for the epoxy to bond to. And so you'll see as I'm going through there, I end up sitting there staring at it for a few minutes as it looks. I'm actually taking sandpaper and scuffing it up. But another thing that we learned in the process of this is that since we have a curved wing, there's not a great way to hold the wing together while it's curing. And so a lot of times we end up setting it up on its end and using gravity to do that. But we've also figured out ways to use clamps in those servo bays, which you can kind of see underneath the wing there towards the end. And that allows it to actually keep a really tight bond between the joints so there's not a gap in between the two ends. But what I'm doing right now is I'm actually inserting those carbon fiber rods. So I believe they're 1 millimeter rods that you soak in epoxy and run all the way down the length of the wing. And then you have to let that cure. And so that's probably the most time consuming step because you have to go through and prep each one of the holes to get that carbon fiber rod to slide all the way down the length of the wing.
I assume those rods are straight, but how did you bend it?
So the rods themselves are actually very flexible because they're only 1 millimeter. So the idea is that they're strong in tension and not anywhere else. So they're actually flexible enough that you can run it down the spar without any pre-bending or work at all.
Thanks, Josh. So past that, there wasn't much that I had to do. It just involved fixing up broken wires from previous flights. And then I realized it took me this long to fix them all. Well, part of it is removing servo wires a little bit to make them a little bit shorter. So one thing that we learned was that the kink design wasn't the perfect design with sweep and taper factored in there. And so what I would do is I would go through and break kinks. And that would just make it so that they were connected cord wise, if that makes sense, but they weren't connected span wise. And it didn't affect the deflection shape that much, but it helped it so that the servos didn't fight as hard to be able to deflect up and down. So right now I'm going through adding connectors, putting the tongues back in the slot. And then shortly I'll be adding in the servos. And we have the servos sitting inside of this little bay. And then we have a laser cut piece of wood that goes over the top and 2 screws that go through that to tension it in there, holding it inside of the airframe. And then the servo rod, and you can come up and look at the airframe. The servo has an arm that's connected to some sort of rod using what's called a Z-bend. But that rod is connected to the trailing edge, and you can see a little bit. Oh, great. But it's connected to this tongue, and it pushes and pulls on this tongue via connector. Then we stick on hatches, and past that, it's putting in the electronics and bench testing, make sure it all works. Before every flight, we do a grounded flight test. So we'll go out and do a range test, make sure that we're able to get the signal strength that we need. And then I will go through a mock flight scenario. So we'll throttle it up to 100% for 30 seconds, and then we'll throttle it back a little bit and fly in some predetermined condition while I'm doing what's called stirring the stick. I'm just moving the control surfaces up and down. And all of that is just to have everything that we can possibly go wrong, have it happen on the bench so that we can fix it before we go into the air.
Would you just kind of walk across the aircraft and show us what's sticking out and what tell us about the electronics and the holes that we have in the airplane at certain places?
So you can see the servo hatches right here. This is actually a cord for the camera, and that's not plugged in because these are just taped on. So you can see over here the ducted fans. We've got 2 ducted fans. That's our propulsion system. And we've got a pitot probe, and that's connected to the Pixlock system. Whenever you're done, you're able to come up and look inside of the airframe. I'll have this open. What holes are you talking about?
So we got the holes on the front up by the nose, little air vents.
Oh, yes, those are for cooling. Yeah, that's a good point. So one of our concerns was we have these ESCs. So an ESC is an electronic speed controller. I am not the most knowledgeable person about them, but from what I understand, they more or less act as the spoon to the mouth of the motor. They say, this is how much current you can have. They make sure things don't blow up. And if you want something more technical than that, you'll have to talk to someone else. But the ESCs heat up quite a bit when we're in flight. And so we were concerned about that. We were concerned about having these, molten pieces of metal that are going to melt through the airframe. They would melt through the airframe. But so we wanted to create these ducted vents. So we have these little holes that come in through the leading edge, and they bleed through into the base section. And the purpose of them is to cool off these ESCs that get pretty toasty when we're flying in. Back behind, we have these holes, and you can come up and look at them. It's a little bit harder for me to explain it. But we have these holes that feed right back into the motor outlet system. So the circulation system is complete. And the air has somewhere to go after it comes into that base section. So we got 3 cameras. One that I mentioned earlier was on that winglet. Then we have 2 on these fan sections that point outboard. And the purpose of that is to be able to really watch these control surfaces in flight, make sure, you know, we've used them for so many different things. For testing and for figuring out what goes wrong in all these crashes that we'll talk about and all this flight testing that I'll talk about later. But
To point out the high angle of attack slots that we made on the.
oh, yeah, this is a recent addition. And this was due to some concerns about a stall glide that we'll watch here in a few minutes or sometime in the near future. But we were concerned about the ducted fans not getting enough power when it was at high angles of attack, so we added these slots in the leading edge of the fan sections. So there's these covers that you can see that go on the fans, and those are just to hold them in there. They provide no real structural support. If you look closely at the skin, you can kind of see these little ripples. And some of those are, well, 90% of them are printing defects, but some of them are due to, we have these, like Josh mentioned, we have these carbon fiber rods that start off about 1 meter, so probably about here. So these carbon fiber rods, there's 4 on the top and 4 on the bottom of this I-beam of that piece that we were passing around. And these carbon fiber rods go through here, like Josh mentioned. He talked about how we epoxy those and stick those in there. But once again, the purpose of that is to provide spanwise support. And we'll pull up a video later of why we needed that. But yeah, so electronics wise, we've got these, like I mentioned, we've got 2 ducted fans, we've got these 2 ESCs. We actually have 3 circuits running on board the airframe. One circuit powers a motor, this motor, and these control surfaces, these 4 inboard control surfaces. Once again, there's 5 on each wing, and then the center section control surface. And then another ESC, this one, controls this motor and these 3 control surfaces and the center section. And the reasoning for that is because this servo for the center section has to be on a 6-volt circuit. And so that's why we had to split that up. And because all the other electronics, so the Pixhawk, that's our IMU system. It's a lot more than that, but that's all we use it for. And then we have this controller board, the teensy, and then we have a receiver. Those are all expecting a 5-volt circuit. So we have those on a different circuit than these wing servos. So the 3rd circuit has these 2 servos, that outboard servo, and then it has all this electronics that I mentioned earlier. There's a separate BEC unit in here that we use. So BEC, and once again, this is not something that I am terribly well versed in, but it's a battery elimination circuit. And so the idea, from what I understand, is to actually, I'm not sure if I am qualified to explain that. If Zach were here, I would defer to him. But I believe the purpose of that is to split off some of this power from these 2 batteries. So power wise, well, I'll finish talking about these different circuits. So this other circuit has got all this bay electronics and those 2 outboard servos and that outboard servo. So plug-in procedure, you want a signal. This is one of the things we learned, but you want a signal going from your controller board to the propulsion system. It's not a good idea to just have nothing going in there. And so what we do is in our plug-in sequence, we make sure all the electronics are on, there's signal going everywhere. And then we plug in the 2 side ESCs. So then we power the left wing, or excuse me, the right wing and the left wing. And that's how power is distributed. Signal wise, everything starts at the teensy board. So the teensy board is our controller board. That's what's running. We have a little piece of code in there that's running the control mapping, that's running, talking to the Pixhawk, talking to the receiver. So this teensy board is controlling the signal, and it splits out the signal. So the signal comes in from the receiver and it goes straight to the teensy. excuse me, and it splits off to the Pixhawk. However, the Pixhawk, all it's doing is reading it in. It's not interacting with the receiver at all. And then, so once it gets to the teensy splits out that signal and it sends a throttle signal to the two fans, and then it sends a servo signal to each of the control surfaces. The cameras are also on that electronics power circuit. And yeah. Any questions? I feel like yes.
I have a lot of questions, but I'll only ask a couple. What's the weight of that fully loaded when it's ready for
½ pounds usually.
1/2 pounds, and what's the thrust on each of those motors?
That's a good question. Together, they are about, ooh, golly, I'd have to remember, it's either 6 or 7 pounds.
6 or 7 pounds?
Together.
Yeah, together.
So
That's pretty high for a 22-pound vehicle, I would think, right?
But we can't hover.
Yeah,
we originally expected them to be a lot more. I think we originally projected that they would each produce about 7 pounds of thrust, 6 or 7 pounds of thrust. But and this is one of those several things that we haven't determined why, but for some reason with our setup, we're only able to produce 7 pounds total. So it was originally way overpowered.
Those motors, what kind of motors are they again?
They're ducted fans.
How is that different than a propeller? And why is the angle of attack important?
That is a good question. So the angle of attack is important because we didn't want the flow to separate over this inlet. So you can imagine if this guy's got some high angle of attack, the flow can separate over the leading edge and it wouldn't quite bend down. I don't know if that's too much of a concern, mostly because of how much these suck, literally. They just pull air in like crazy. And so I don't, yeah. But that was the reasoning behind it, was that we were concerned about the flow separating over the leading edge, and so we wanted the fans to be able to get something if we were in that stall.
And how is it different than a propeller?
That is a good question, and I will defer to someone who knows more.
The ducted fan is just a shrouded propeller.
It's just a what?
Shrouded propeller, meaning that it's got a casing around it. So
So it is a propeller.
yeah, it's
Get a little more suction by putting a shroud around.
Yeah, exactly. You increase the efficiency a little bit, and they're kind of more popular in jet RC aircraft. So, you know, they're like an F-16 or whatever you want it to look like an F-16, and you've got, you know, your ducted fan inside of there where the engine usually would be.
Yeah.
So anyway, that's where you see them most. They're not very efficient compared to a propeller.
Really?
Yeah, because you have, basically, it's a really low aspect ratio wing inside of that that's spinning around, right? And so props are really efficient because it's a long aspect ratio wing. So they can generate a lot of power for very little.
But you need a lot more space.
Yeah, exactly.
Yeah.
Right. And the reason we didn't go with the prop is because we don't have a landing gear on this, and takeoff and landing is tricky when you have a propeller and no landing gear, because you have to keep your prop off of the ground a certain distance. And so that's, and also for launching, ducted fans are safer because you don't have to worry about students' fingers getting caught in there launching, right? So anyway,
That's worse than a beheaded student.
That's how you carry an insurance policy, right? Is the overall design strategy to kind of iterate with the 3D printed and then eventually manufacture something when you get to the right design?
No.
This is a research vehicle,
Okay.
not a production vehicle, and we've come a long way on it. But you know, the entire point of this vehicle was to demonstrate yaw control with a single wing.
Okay.
So roll, pitch, and yaw control actually with just a single wing. And so that's, you know, that's the sole purpose of it. So we do have all of these files are available online on our website, so you can go print them yourself or scale them up or down and, you know, reprint. And we actually have 2 airplanes up there. Yeah.
Sorry, we missed the first part
Yeah,
of
that's
the meeting,
okay.
I'm sure.
Yeah.
What's the total material costs? Just for the structure, no electronics included. It's a total material cost for.
Material cost.
building
So
this.
it's $80 for 3 kilograms. And it's probably 3 reels of kilogram, 3 reels of filament. That sounds a little high to me. I think it's actually something more like 2. I want to say it's somewhere around $500 to $600 of plastic.
Yeah,